So whenever you're asked to find how many electrons are to be removed to make a particular charge, easy thing, that charge divided by the charge of the electron. Is that clear enough?
So since it's removed, it's not negative then?
If it says must be removed, that means it's positive. When you remove electrons, what's the charge left behind? Positive. And there I've put negative for both. It doesn't matter there actually, because you're only asked to find the number, the number of electrons. So can I have such a question on the exam and be sure that you get it? Look, there's no answer for anybody. Can I have a question like this? Something like this?
Yeah.
How many electrons need to be removed to make a charge of 2 microcoulomb? Will you be able to do that? Yeah, just 2 times 10 to the negative 6 divided by the charge of the electron. And you're always going to have a big number. Just remember that. Big number. All right. Go to the second one. This is the second question. We'll try to do it together because it's not anything like we did before. So please pay attention. A 50-gram ball of copper has a net charge of 2 microcoulomb. What fraction of the copper's electrons has been removed? Now that's making it tough. You know why? Because first you have to find the number of electrons removed, and then you have to find what was already there and divide them to get a fraction. Do you know the meaning of a fraction? Mm-hmm. Yeah? If I have $10 with me and $5 are removed, what's the fraction that was removed? 1/2, 5 by 10. So what did I do? What did I have to do? First, I had to tell you how much was given away. And then I had to know how much I had. Are you with me? And then I have to divide what I gave away by what was there. That's what I'm saying. So be with me. So to answer this question, what fraction of the copper's electrons has been removed, you would have to know what? You would have to know 2 things. What? Number 1, you have to know how many electrons were removed. And number 2, you have to know how much was originally there. Right? That's what I'm going to do. And then you're given information. Each copper atom has 29 protons, and copper has an atomic mass of 63.5. You see everything coming in, chemistry you may say, but it's physics. So how do you do this? And I suggest that you don't write while I'm explaining. All right, number of moles of copper. Now, a number of moles. What do you mean by a mole? What is 1 mole? Anybody taken chemistry here before you came to this class? Let me see your hands. All right, some of you have not. The atomic number of an element in grams is 1 mole. What is the atomic number of copper? Say it. Am I all alone here? What is the atomic number of copper? 63.5. So if you have 63.5 grams of copper, you would say you have 1 mole of copper. So write that down. 1 mole of anything is equal to its atomic number in grams. 1 mole means atomic number in grams. I think that makes it easier. So the number of moles of copper, N is the number of moles, is the mass that you have divided by the atomic number. So 50.0 divided by 63.5 gram per mole. You also have to, you know why I put 63.5 gram per mole? I told you. Each mole is 63.5, right? So when you divide that, I did not get that number. I just didn't want to do calculations. Next, we're going to find the number of protons. How do you find the number of protons? Hello, each copper atom has how many? So what do you have to do? Correct? Find how many atoms. And then multiply that with 29. There you go. Okay. Number of protons, I called it NP. Going with what we said just now. I suggest Can you listen and write? If that's the case, you can do both. But it's more important to understand. What would we say? We could do it this way. We could first find how many atoms and then multiply that with 29. But there's an easier way. There is something called the Avogadro number. 6.2. Very good. 6.02 times 10 to the 23. What's the Avogadro number? Avogadro number is the number of atoms in 1 mole. Write it. If you don't know, write it. Avogadro number is the number of atoms in 1 mole. So we have a shortcut now because we already found the number of moles, didn't we? Well, we didn't get the number, but we have it there. So if you multiply that with the Avogadro number, you automatically get the number of atoms. Okay. Did everybody write that? Avogadro number is the number of atoms in 1 mole. Okay. So you have these many moles. Did somebody get this number? How much is that? 0.8? 0.7. All right. So we have that many moles. And if you multiply that with the Avogadro number, you will get the number of? No, not the number of protons. You get the number of atoms, which you will have to then multiply with 29 to get the number of protons. Okay, so I did all that in one step. That's the number of moles. That's the Avogadro number. That's the number of protons. Are you with me? So you multiply all of them, you get the number of protons as, well, now I'm putting the numbers and calculating. That's the number of moles. This is the Avogadro number. Then multiply that with 29. You will get the number of protons. I've also put the units there for everything. So, is this what you get? If you did try, did you get 1.375 times 10 to the 25? Is that the answer to the question? No. No. What do you do next? You have to find how many electrons have been removed, which we know how to do, right? How? Hey, what's the charge? 2 microcoulomb. How many electrons have to be removed? How do you do it? Tell me. Yeah, 2 times 10 to the negative 6 divided by 1.6 times 10 to the negative 19. That will give you. All right, so next step. There I put NP is equal to NE. What is that? Because the number of protons is exactly equal to the number of electrons. So I just put that's the total number of electrons that were there. So remember I told you for the fraction we need to know 2 things. What? How many were removed and what was originally there. Correct? So I got the number that's originally there. Now I'm going to find how many were removed. Okay. And that we know. Which is our question number 1. I don't want to take too much time on that. Number of electrons removed is the charge divided by the charge of an electron. So that's, because it's in microcoulomb, it's 10 to the negative 6. And then divided by the charge of the electron. So you get 1.25 times 10 to the 13. Now, what do you have to do next? Last step. Divide. Yes. And so to find the fraction, divide the number removed by the number that was originally there. And if I were to ask a question on the exam, would it be number 1 or 2? 2, because in 2 you also had to do. This is the toughest problem I can ask you on this. So you know what I'm looking for. If somebody can do this problem, I'm really happy. But I would change some things just to check whether you're understanding. That's all I can do. Change some numbers most of the time. And there you have it. Okay. The distance between how many charges? 2 charges. And so you say, oh, the force is given.
Looking for R.
You're looking for R. Okay? And the two charges are given?
Yeah.
Yes.
Huh?
You get those
What's the law? Which is the formula? What's the formula?
K, F equals K, Q1.
There you go. F is equal to K, Q1, Q2 by R squared. Plug it into that.
We just use that K, that constant.
8.9. That's right. That's right. So to save time, I'll do it for you. I mean, if you've understood, why should you take time to calculate and write unless you can do it fast? Okay. So what I did is, whatever you have to find, I made that the subject first. Are you all clear on that step? I just cross multiplied because you see a 1 here, rearrange. Is that right? I've seen some students get this backwards. That's a terrible mistake, putting that backwards and losing all your points on the exam. Substitute the numbers. All right, speed it up. Square root of that, so that's, put the value of K. Remember, it was nanocoulombs. Why did I square that?
Because it's the same value.
Yes, there are two of those, isn't it? So instead of saying Q1 times Q2, same thing as putting a square there. And that's the answer I got. Did you get that, somebody? Well, I'm not giving you time to calculate, so. Got it? Very good. So number 3 done. Now, usually a test charge is +1 coulomb, unless otherwise specified. In this case, it says a test charge of +2 microcoulombs. See? So you have to imagine that is kept there.
Does it matter what side?
It does not. Which side? No, it does not. So you have a test charge +2 microcoulomb, which is placed halfway between +6 and +4, isn't it? Separated by 10. So a diagram I thought would, and yes, Q1 and Q2, one is 4, the other 6. It doesn't matter which side you have, which one. It's not going to change the answer anyway. And then the test charge is Q, exactly midway. Okay. Right. So you know how to do this, don't you? Find the force. What? Find the force on the 2 microcoulomb due to each one, and then think about the direction and either add or subtract. In this case, what are you going to do? What are you going to do? The force on this 2 due to 4 would be in which direction? To the left or to the right? To the right. And the force due to this here would be to the left. And which force would be greater? Of course, the force due to this. Correct? So would you have to subtract or add? Subtract. The force due to 6 on this would be to this side. The force due to 4 on 2 would be to the right side. So you subtract. And that's exactly what I'm doing. Wait, how do you read that? How do you read that? Force on 2 due to 4, isn't it? Or by 4. Okay. So that's the formula. I didn't want to write it twice, so I just wrote the formula there once and substitute both into that. Get it out of the way. 10 to the minus 6 because it's micro. Wait, why 0.05?
That's half.
Half of 10 is 5 centimeters, and then divide by 100. Okay? 5 centimeter divided by 100 is 0.05. That's why you have it there. And then calculate. The first force is 28.8 newtons. Can I put per coulomb there? No, because it's not on 1 coulomb. See? It's on 2 micro. So you can just... And then the next one, the same. Likewise. Force on 2 due to 6. Same thing. And same distance, and you get 43.2. It's in since you know the directions and I didn't label it, I can label it even now. So there, is that the direction of one force? Right? And the direction of the next is opposite direction, but okay, just a little bigger. So the net force would be the difference. The total force is 14.4 newtons to the left. There is a B part to this question. The B part is, what is the direction of this force away from or toward the 6 microcoulomb charge? What's your answer? Away. Why? Because which force is bigger? Isn't this force bigger?
Yes.
So when you take the difference, you're taking a bigger one, take away the smaller one, so you're going to have something remaining in this direction. So I didn't even see the B part. But we talked about it. We talked about the direction.
So you said the 28.8 is?
I forgot. In this question, didn't it say the electrostatic force between two protons, at what distance would it become equal to the weight of a proton? You see what I did?
Yeah.
This is the electrostatic force. On the left side, you have the electrostatic force due to two protons, and that's equal to the weight. So that's how you do it. Problem done. So the electrostatic force on the left side, this one, should be equal to the weight. Everybody there? Are you getting it? There you go. All right, so since you have to find the distance, I made that the subject. I hope everybody gets that math part correct. And then you have to find the square root. But did you know that square root means raising it to half? The same thing. So either put square root and then plug in the numbers. Wait, isn't that the charge of an electron? Because the proton and the electron have the same charge. Okay. And I squared it because there is Q1 times Q2, both are the same. Okay. Then the mass of the proton that I gave you times 9.80, you calculate it to be 0.119 meter. Done. All right. So where can a third charge be placed so that the net force on it is 0? Okay, did you notice that one is positive, the other is negative? Okay. And so that's the 5. Saying that's the negative 3. I think I should do all this. Okay. So since I was not recording when I was saying all this, that's how you get the answer. But you heard me say it. I mean, it's just I forgot to hit the button there. You know, what I wanted you to see is not the math. Forget about the math. I wanted you to see that if the charges are opposite, then where you get 0 force is going to be not between them, but outside them. Did you get that? Mm-hmm. That's fine. That's all I wanted. Forget about the math. That's not going to be in the exam. Shall we go to the next? Because when I say that's not on the exam, then you scratch it out, right? Don't do that, but... Now, if you cannot do this problem, I will be sad. The A part. Remember, the word magnitude means the number, right? So it means what charge, what amount of charge creates a 10,000 Newton per Coulomb electric field. Oh, you have electric field at a distance. So you have given the distance and you have to find the charge. What's the formula that you were talking about before? Isn't that the formula that you apply now? What is the formula? E is equal to, yeah, F over Q is equal to K Q1
R squared.
Q by R squared. I don't know if it's using caps K, I think. On the formula sheet, is it caps K? It's small k? I mean Q, I mean Q.
It's uppercase Q.
Uppercase, that's what it's thinking. That's on your formula sheet. So E is electric field or intensity. So that's why I said I'll be sad if you cannot do that. So what all do you know? I mean, you can take this out of the equation because you don't need that there. That's just how you get that. So it's E is equal to KQ by R squared. Wait. You know, I never spoke about that until she brought it up. But I was always using this, remember? Isn't this what I was using? Remember that? What's that? Why? If you hear the word field, what do? Then it comes back to the same thing. That's why I didn't want to bring that in. It's so much easier to. It's a force. If this is 1, you can as well write this as E. That's the difference. You know, if it's 1 here, this is E. F and E are the same. So use this. All right. Do you know this? How much?
10,000.
10,000. You know this, and you're asked to find the charge, correct?
Mm-hmm.
All right, and you're given the distance. There you go. That's it. You know this. You know K. You have to find Q. So, you think that's tough? No. Is KQ by R squared or this KQ by R squared? Doesn't matter. Make Q the subject. 10,000, 0.250. Don't forget to square it. Divided by K. And you get that. 6.95 times 10 to the negative 8 coulombs. This you should be able to do. All right. How do you do the B part? It's just the same question. Now, yeah. How large is the field at 10 meters? Correct. Change the distance. But now you know the charge. What is the charge? Yeah. So now you do this again.
With the Q1, Q2?
Yes. But remember the Q2 becomes 1. Yeah. That's it. Yes.
Like the distance, then you assume that that's already the radius. You don't divide it by.
The radius is not a correct usage there. I know why you're saying radius because it's an R.
Yeah.
That's distance, yeah.
So like you just assume that is what you use for the R value.
No. Distance is always the R value.
Okay. So but when it's separated by, that's when you like divide it in half because the point charge.
Well, it's separated and then you have something like what's it at the middle.
Okay.
So that's when you divide. 7 done, 8 and 9. I kind of tried to mix the problems up, thinking about the assignments that you have to do. See? I tried to set it up in such a way that if you understand this, you should be able to do the assignment. Well, it won't be exactly the same, you know. Please read the materials, the sections and all that. Go back to the text, and if you find it really tough and nobody can do it, I've not put questions like that, then we can, of course, discuss it. I mean, it's okay in the class. All right, 8. How do you do that? Anybody heard of a Van de Graaff generator? We're going to see that. You've not seen a Van de Graaff generator? You know, I'm sorry for making it look like bad. You've not seen it. In school, like, you have seen a, I mean, because kids like to play with that. Whenever we set up physics experiments, that's a big sphere which has a running bell. You will see it, and you will see it working too. You will touch it, and I'll see that you get an electric shock, which won't finish you off, but you will see it. It's all there. You'll see that. So it generates a lot of electricity and charges you. If you touch it, like she will have her hair standing up. Or, you know, straighten hair. Well, I don't have any more to stand up, but you will see that it gets charged. And then in school, what we would do is we would make all the students stand in a line, and this person is on an insulating stand touching the Van de Graaff generator, and you see the hair standing up, and then slowly, because poor kids, they don't know what's going to happen, you say, hey, touch. So this person on the insulating platform touches the first one, and they're all holding hands. Guess what's going to happen? Everybody will go like, oh! Because the charge immediately goes to them, you know, to the ground. So that is the Van de Graaff generator. That's what's given there. Wait. I want to make it a little bit practically interesting. North Korea is in the news. Nuclear bombs. You know that many countries, including ours, have a lot of nuclear bombs, right? Have you ever thought about it? How do you build a nuclear bomb? What's that? I think I mentioned it once. You have to break a nucleus into two. What? What did I say just now? Cut a cake? How big is the nucleus? And someone like, break it into, or get a knife, chop it. It's so small. How do you break it? To break it, you need a fast-moving projectile that you cannot throw a stone at it. You either need a neutron, which is easier to accelerate, tougher to accelerate because it has no charge. But if it's a proton, it'll accelerate. That's our next chapter, but I just wanted to, I'm not teaching you the next chapter. Someone like, he's crazy, he's going to teach us 3 steps. So if you have something, let's say you have 2 plates, one positive, okay, and the other negative, and you put a proton here, what do you think will happen to the proton? It's free to move. What direction will it move? To the right. I had to say that to talk about the question. So initially it's not moving, but now it's going to have an acceleration, isn't it? That is what you're asked to calculate. So if the proton is kept in a field, an electric field, it's going to accelerate. You just think about the car, and if you're in a race, you know, going off from that signal, the red light changes, you want to show off, just whoa! Haven't you seen 2 people do that? That's what you're talking about. And then, if you keep on accelerating the proton, its speed becomes so high that if it now hits a nucleus, the nucleus divides into 2. Are you with me? And then, what comes out is a lot of energy. We learned that the hard way when we dropped the fat man and the little boy. You know what those are? Those are the nicknames of the 2 bombs that were dropped on Hiroshima and Nagasaki. Had a size of 80 centimeters only. The death and destruction caused by that, nobody believed would happen. I mean, we would not have done it if it was Pearl Harbor. You know the history right behind it. But we would not have done it because nobody believed. The 2 scientists who built it, 2 Germans, Otto Hahn and Strassmann. This guy, those are the guys who made first found nuclear fission, which is breaking the nucleus into 2, right? And then this German scientist fell for the money that we offered him. Green dollar bills. He came and he built the atom bomb for us. Do you know why electricity is cheap in this country? And someone like, cheap? Yeah, compared to the 3rd world countries. Very cheap. Because we get our electricity from nuclear reactors. What's the difference between a nuclear reactor and an atom bomb? One is controlled, the other is uncontrolled. I hope you got the difference, did you? An atom bomb is uncontrolled reaction. You've heard of the chain reaction? I know, I'm just throwing in those numbers. And all of these explosions take place together, just like a chain. All that energy coming out just can dry us up like not even powder exists. So much energy. 1 kilogram of a nuclear bomb produces as much energy as 50,000 tons of TNT. You know what TNT is? Okay. 1 kilogram of nuclear material produces as much energy as 50,000, I did not say kilograms, I said tons. 1 ton is 1,000 kilograms. Are you getting the numbers? Today's bombs that we have are enough to just simply make countries vanish off the face of the earth, believe me. 1 atom bomb. That's why it's scary. Because all it takes is a madman. Because if 1 mad person does it, we would have to, you know what I'm saying? I mean, I don't even want to say it, but what do? That's where all this comes in. So go back to that problem. I got you all interested. It's like, okay. All right, do that. Come on, we need to get out. Calculate the acceleration of a proton in that field. What? There's nothing given? All right, how do you tackle this problem? How do you... No idea? So F is Q times E. Q is the charge of the proton, which is the same as the charge of the electron, times the field. Find that. Okay? And then use F is equal to mass times acceleration. Rearrange that to make acceleration the subject. Divide force by mass. And of course, you're going to divide by the mass of the proton, which will be given to you, which is 1.67 times 10 to the negative 27. And when you do that, you will get a number, and if you are not surprised, well, which means you're not looking at the number. Look at that number. Look at the acceleration of the proton. Look at the acceleration of the proton, big or small? Big. Do you know how we have the television, at least the older ones? Now we have the LEDs and all that. But still, do you know that in a television set, electrons are bombarding the screen, and that's what produces that light that we see? Did you know that? No? Electrons and protons can be accelerated easily. So look at that acceleration. So that's how the picture is produced. I wish I could, in 2 minutes, tell you how a television works. I cannot. Do you know when the television was invented? What's the direction of the electric field in that problem? Horizontal. Thank you. I don't blame them. I'm so tired now. Can you see? I can't even see now. I'm so tired. The electric field is horizontal, isn't it? It says that. Is it from left to right or right to left? Doesn't matter. It doesn't say it. Doesn't. All right. So you have something hanging down there. Stop. Okay. Here it is. So you have an insulating ball that's hanging. Hey, where's the string?
T is the string.
This is the string?
Yeah.
But I thought when you have a ball and a string, it's going to hang straight down. I mean, that's what I'm thinking. If you have a ball at the end of a string and tie it to the ceiling, wouldn't it hang straight down? But there's an electric field here.
Yes.
Now, if there's an electric field and this thing, is it charged? Is the ball charged? Yes, it is charged. Is it positive and negative?
Positive.
Positive. And the field is horizontal. Are you with me? Field is horizontal. So that means, let's imagine that the field is to the right. It is.
Yep.
It is. That's why the positive charge object is moving to the right. Well, let me just tell you. A positive charge always moves in the direction of the field. That's our next chapter, but I just told you. A positive charge moves in the direction of the field. A negative charge moves opposite. Okay. So this is positive. The field is this way. So the string was like this. Yes. But due to the field, there is a force acting on it. That's what is making it hang like that. Everybody got it? So right now it's hanging like that. And is it moving? Or is it just there?
Just there.
If it's just there, then all the forces acting on it are balanced. What are the forces acting on it? For sure, it's weight. What direction does the weight act in?
Down.
Vertically down. I like that better. Vertically down. So the weight is mg, you can see. And then what's the other force? The force, the electrostatic force, which I told you is to the right side, didn't I? And do you know how to calculate that force? Yes, we know. K, Q by R squared. Come on. So we have two forces to the right, electrostatic, and the weight. And because this is not moving, there should be an equal force up and to the left. Where does that force come from? It comes from the tension in the string. The tension in the string, oh, the arrow is there. I thought there was not. You see that? It's upwards. That is broken into two. 1, 2. Now, do you know why it's sine theta and cos theta? College Physics 1. If you need more help on that, come to me. Right now, we got to finish. So, am I right if I say T cos theta is equal to mg? And T sine theta is equal to Fe? Will I be right? That's what I'm going to do. Let's see your hands if you understood. Oh, 3 hands up. Okay, never mind. Thank you. T sine theta is equal to Fe. And what do you get if you divide sine theta by cos theta? If tan, yeah, you get tangent. Sine by cosine is tangent. So that's what I'm going to do. That's why you divide one equation by the other. The t's got cancelled. Okay? And sine theta by cosine theta is tan theta. And so I have to do the same on the right side. So QE by mg. And I forgot to, when I started doing this problem, and I said you cannot do it without the angle. So take this angle as 18 degrees. It's given. You cannot do it otherwise. Take it as 18 degrees. What are you looking for?
Q.
Q? No, E.
E.
Because Q is given. The charge is given. You're finding the strength of the field. So that's E, right? Okay. So plug those numbers in. And this is what you get. Substitute that. Y times 10 to the negative 3 grams. You have to change it into kilograms. Right? So you have to divide by 1,000. That's why the mass is in kilograms. Right? 5 divided by 1,000 or 5 times 10 to the negative 3. 9.8 times tangent of 18 by So that is the answer that you get.